Welcome to This Explainer. Okay, we've got something seriously mind-bending today. We're breaking down a major breakthrough published in the Journal of Alloys and Compounds. It turns out, researchers have actually found a way to take common, everyday rust and completely re-engineer it into a solar-powered fuel factory. We're talking about a microscopic machine that literally eats carbon dioxide for breakfast.
I mean, really think about it. What if CO2 was fuel? Imagine a world where the very gas that's, well, kind of suffocating our planet right now becomes the exact fuel that powers our cities. It will completely flip how we view this supposed waste product. We've been told for decades that carbon dioxide is a looming global threat, but what if we could reframe our entire approach and actually create tremendous value from it?
So, here is our game plan for today. 1. The green energy roadblock. 2. Enter engineered rust. 3. The Goldilocks tin recipe. 4. Stretching and breaking CO2. And 5. A circular carbon economy.
All right, kicking things off with Section 1, the green energy roadblock and the dual crisis of our time. To truly appreciate why this breakthrough is such a game changer, we have to acknowledge the massive hurdle we're facing. We're dealing with a terrifying double-edged sword here. On one side, our climate is severely threatened by rising CO2 emissions, and on the other, the fossil fuels we heavily rely on to run our daily lives are just vanishing. This isn't just some abstract scientific issue. This is the core problem affecting every single one of us on a daily basis. For years, scientists have been chasing this kind of holy grail solution to overcome the crisis, and it's called photocatalysis. This is basically the process of using sunlight to drive chemical reactions, like breaking down nasty pollutants, or even better, turning CO2 back into fuel. The dream has always been to use sunlight-catching materials to do our dirty work. Essentially letting the sun power our chemical factories.
But there's always a catch, right? There's been this massive roadblock preventing this dream from becoming a widespread reality. Most materials we've tried in the past, like titanium dioxide or zinc oxide, they just fail. They either can't absorb enough visible light to begin with, or they suffer from what's called the recombination problem. This basically means the solar energy they do catch simply cancels itself out immediately. The energy just vanishes in a flash before it can actually do any of the useful work required to turn CO2 into fuel.
Which brings us to Section 2, Enter Engineered Rust, and Jingru Yao and Shipin Li's breakthrough.
So how did a team of international researchers bypass those past failures? Well, with a pretty bold strategy. Instead of relying on dirty, rare, and ridiculously expensive precious metals like gold or platinum to act as catalysts, this team shifted gears completely. They turned to earth-abundant, super cheap materials, iron oxide and tin. They literally looked at the humble, everyday stuff you'd find on decaying bridges and old pipes, and somehow saw the future of green energy. Now, they obviously didn't just scrape some standard iron oxide off a rusty pipe and call it a day. Using phase engineering and tin doping, they created an entirely new, smart structure. They built a core shell heterojunction. Think of it behaving exactly like a piece of microscopic candy, with a hard shell and a soft center. At an atomic level, they engineered a magnetite core perfectly wrapped in a magamite shell. This highly specific architecture is what allows the material to finally clear the hurdles that plagued all those older materials. And honestly, this next number brilliantly illustrates the power of their design: 87%. In the world of environmental cleanup and chemical engineering, hitting a number like this, using just cheap, earth-abundant materials, is absolutely staggering. So let's look at exactly what that 87% represents. This engineered rust is a total dual-threat catalyst. Not only did it absolutely crush 87% of a common antibiotic pollutant in water in just 100 minutes, but it also achieved something even more vital for our energy crisis. It successfully converted CO2 into carbon monoxide, which, by the way, is a critical precursor for synthetic fuel, at double the rate of previous benchmarks. Moving right along to Section 3, the Goldilocks tin recipe, finding the molecular sweet spot. So how exactly did they cook up this miracle material? The science relies on a one-step solval thermal method. It's actually a pretty elegant process. First, you mix the iron and tin together. Second, you place them into a high-temperature, high-pressure environment, so basically acting as a chemical slow cooker. And third, this highly controlled environment allows them to systematically grow these tiny, super precise octahedral crystals right from the ground up.
Now, all of this relies on a highly specific and honestly kind of counterintuitive number: 0.4. I know, it sounds incredibly small, but in the world of molecular engineering, precision is quite literally everything. This exact decimal completely makes or breaks the entire chemical reaction.
You might naturally assume, hey, if tin is the secret ingredient making this rust so powerful, dumping more of it in would make it better, right? Well, it turns out that is totally wrong. Adding more tin isn't better. Exactly 0.4 millimoles is the absolute sweet spot. Add too little, and the reaction is frustratingly slow. Add too much, and you actually start to create these structural defects that just kill the performance. But at exactly 0.4, the tin ions slide perfectly into the iron lattice and successfully transform the outer layer without destroying the crystal's integrity.
That precise 0.4 recipe, that is the secret to beating the recombination roadblock we talked about earlier, creating a unique structure known as a type 2 band alignment. Just think of it as a microscopic slide. When the sun hits the crystal, it generates electrons and holes. Normally, they just cancel each other out instantly, end of story. But this specific structure forces the electrons to run out to the shell, while the holes are pushed deep into the core, keeping them far apart. Because they are physically separated, they actually have the time they need to travel to the surface and do the hard chemical work.
All right, Section 4, Stretching and Breaking CO2, the molecular hooks.
Okay, so even if you manage the energy perfectly on the inside of the crystal, how does the CO2 actually stick to this microscopic slide to begin with? The answer lies in oxygen vacancies. By adding that ultra-specific amount of tin we just talked about, the researchers intentionally created missing oxygen atoms inside the crystal structure itself. These intentional vacancies act like highly active chemical magnets, or little hooks, that just snag the CO2 molecules directly out of the surrounding environment.
The physics happening here are just wild. Before the reaction, a standard CO2 bond length is about 1.18 angstroms. But the instant it latches onto those oxygen vacancy hooks, it stretches out to 1.32 angstroms. The CO2 molecule literally physically stretches upon hitting these hooks, pulling the carbon and oxygen apart before the chemical reaction even officially starts.
And why is that physical stretching so profoundly important? Because stretching the molecule lowers the energy required for the reaction by more than half. Seriously, because the bond is already pulled taut, it makes the whole process incredibly efficient. It requires way less solar energy to finally snap it and convert it into fuel. It's essentially doing half the work before the sun even finishes the job.
Which brings us to our final section, Section 5, a circular carbon economy and scaling up the solution.
Moving out of the microscopic world for a second, let's look at the massive industrial implications. If you're sitting there wondering if this is just some fragile lab experiment, the answer is a resounding no. This solution is exceptionally pragmatic and powerful because this engineered iron-based catalyst is inherently magnetic. Think about what that means for a massive industrial plant. You absolutely do not need expensive, complicated, easily clogged filtering systems to retrieve this catalyst from the reaction mixture once the job is done. You literally just drag a large industrial magnet through the mixture and pull the catalyst right out of the water. Boom. Done. And amazingly, there is zero loss in stability. In their testing, the material survived 6 full cycles and was just as strong and stable as it was on day 1.
So, let's pull everything together with our key takeaways from this explainer. First, this proves we can officially ditch those rare, dirty, and expensive noble metals in our pursuit of green tech. Second, we are shifting to a really powerful phase engineering mindset, where we're building smart structures that manage energy right down at the atomic level. And third, this technology totally lays the blueprint for on-site, large-scale CO2 recycling, where industrial plants could literally capture and convert their own emissions into fuel using just sunlight. This proves we can solve massive, global problems using smart atomic structures and the most everyday materials. So I leave you with this final thought. What other basic signs of decay around us are actually the hidden blueprints to our sustainable future?